so we've been working with complex numbers and with the idea that if I tell you what the roots are, then you know what the factored form and what the standard form of the quadratic is. And I want to do an example first where if I tell you the real roots, you can figure out what the original quadratic is. So let's say that I had real roots of, let's say, 3 comma 0 and negative 2 comma 0. What I can do is build up factors like x minus 3. See how that hits the root 3 comma 0. Notice it was positive 3, but I wrote x minus 3. And then the other one is x minus negative 2. Or I could write x plus 2. And you can see that if I multiply those two factors together, then I get a quadratic that goes through both of those. And if I distribute that out, you can see it goes x times 2, negative 3 times x, negative 3 times 2. So we should get x squared minus 3x plus 2x minus 6. I'll type it in standard form, x squared minus 1x minus 6. And the pattern is something that we've talked about a bunch of times. Should feel pretty familiar that the two factors add to make the b term, and they multiply to make the c term. So what I do is I write x minus root, and then I look at what the factors are, and those factor numbers are going to be the opposite of the root numbers, right? Root number was positive 3, factor number was negative 3. Root number was negative 2, factor number was positive 2. And then I notice that those factor numbers add to make b, multiply to make c. Okay? One other thing that we talked about is that if you have a complex root, then you also have to have its conjugate. And where does that idea come from? That comes from the quadratic formula. And if you look at the quadratic formula, I want you to notice that this part and this part are both real parts. So the only possible part that could be imaginary is if we have the square root of a negative. So this part right here is the only possible imaginary part. So if, and only if, the b squared minus 4ac is negative, that's the only way we'll get a complex root, because that will give us a negative number when you take the square root of a negative. And so that means that we have to, there's no other option, we must have conjugates, because it's going to go plus the imaginary part for one of my roots and minus the imaginary part for the other root. And so that sentence that you all should write in your notes is just that complex roots always come in conjugate pairs. Okay, so that's all the background information you need. Now I'll do two examples. So let's say that I give you one root. Let's say that the root R1 is 2 plus 3i. Well, I know that if there's a plus imaginary number, that my other root must be 2 minus 3i. So we're going to give you one root, and you're going to have to figure out what the other root is. So now I know that my factors look like this. X minus the first root and x minus the second root. Because that's what we did when it was all real numbers. We just did x minus root and x minus root. I'm going to distribute the negative to get that. And double negative 3i, like that. You'll see that there's still conjugates even after you distribute the negative. I'm going to do this one the slow way, and then I'll show you the shortcut again. So the slow way is to go multiply 9 little pieces. X times negative 2, x times 3i. Then negative 2 times x, negative 2 times negative 2, negative 2 times 3i, then negative 3i times x, negative 3i times negative 2. I always run out of space. And then negative 3i times 3i is negative 9i squared. Notice that I squared is a real number. It's negative 1. When you simplify this, you get x squared, combine, minus 4x, cancel, cancel, plus 4, and plus 9. And where did the plus 9 come from? From right there. Negative 9i squared is plus 9. And so this quadratic, if I write it out in its standard form, is x squared minus 4x plus 13. And what you'll notice is that it does not hit the x-axis. And we knew it wouldn't hit the x-axis at real numbers because its two roots are complex conjugates. You'll also notice that the vertex is at 2, 9. Where does the 2, 9 come from? 2 is the real part, and 3 squared is the 9 right there. 4 plus 9 makes 13. So the shortcut is the 2 and 2 make the 4. They add up because the negative 3i and the positive 3i add up to make 0. And 2 squared makes 4. 3 squared makes 9. So I'll show one more example, just a little bit quicker. Let's say we had one root of 7 minus 5i. We'll make it negative 7 minus 5i. Then I know our second root is going to be negative 7 plus 5i. I know our factored form is going to be x minus the first root and x minus the second root. I can distribute the negative. And I can say my standard form is going to be x squared. 7 plus 7 is 14. 7 squared is 49. 5 squared is 25. So x squared plus 14x plus 74. And if I showed you a graph of that, you might be able to predict, it's a little hard, you might be able to predict where the vertex is. Let's zoom out, zoom out. No real roots. Vertex is at negative 7 and 25. Negative 7 comes from the real part of the roots. 25 comes from the imaginary parts being squared. So thanks for watching. Let me know if you've got any questions, and I'm happy to help out.